and this comes from one of the demos. I think this was the R file in week 10, right? So a lot of these commands are, what you have to do is modify the matrix, right? You have to modify initial conditions, and parameter values is where you have to modify the matrix. So that's right. That's what you do for your question, right? So if in this, so we're working 3 questions, and then we're gonna work on question 9, okay? So question 6 and 7 are 3 by 3. Question 5 is 2 by 2. So in questions 6 and 7, there are 3 groups, and in question 5, there are only 2. But if you had more, like I think question 9 has 5 groups or so, then you have to remember here, you create a matrix first with all zeros, and then it's squared. So it's the number of, whether it's 2 by 2 or 3 by 3, you create a matrix with zeros and that number of columns and rows. And then you have these variables called beta 1, beta 2, beta 3. So if you had more, you need beta 4, beta 5. So you want to specify all the things on the first row, and then later you collect them in that list, and that's what you define as the first row. And then you have to go, these are Leslie models, so there is a lot of zeros, but then P1, P2, P3, P4, they're located in the sub-diagonal entries, and you have to update what those values are. Once you define that variable, a.matrix, that's what you use to call this function, which is going to iterate, right? So let's see what this looks like for question 6. So we can run this, and there's a lot of output here, and part of this output. So let's see, the very first thing is this v.sim. You know, I can call that something else, but so that's what's being plotted. So what is v.sim? Okay, so that has 2, with a dollar sign, it has 2 things here. One is called numbers, one is called fractions. So if we look at the numbers, right, this is going to be, what do you guys think? This is a column, a matrix, this is a scalar. What's going to be this output? Matrix. It's a matrix, right? Should be a matrix. So when I hit enter here, there you go. How many columns? You have as many columns as the number of groups, okay?
Okay, so we started with this matrix right here. I was able to calculate the characteristic polynomial by subtracting the lambda values from the diagonals of the matrix and then setting the determinant equal to 0. Yeah. That ended up giving me this.
So just right there on the one side, right? Or maybe on the left of that polynomial. That's the determinant of a minus lambda I.
Mm-hmm. Oh. Determinant of a minus lambda I
and
equals 0.
Well, right. Right, from that equal to 0, that's where the bubble comes from, right? That's okay.
Right.
And then the roots of that cubic.
Right. So honestly, I did that, like, I did not try to find these. I just used the eigenvalue decomposition that's given to you in R. I actually had to realize that I put the matrix in incorrectly a second ago, so I had to redo everything. But I still have it. So I used just eigen of the matrix to give me these eigenvalues. So this is lambda 1. Yeah. This is lambda 2. This is lambda 3.
So they're equal, like next to each 1.68.
And then these are the corresponding.
That's V1, that's V2, that's V3.
Right. These are the eigenvectors corresponding to each one. So the next part it asked about was which is the dominant eigenvalue. So these two are both the absolute value of V2 and V3. No?
No, that's the absolute value of lambda 1, the absolute value of lambda 2.
Or that's what I meant. I'm sorry. Yeah, you're right. Yeah. Thank you. These are the absolute values of the other two eigenvalues. So
But it's, they're not, I know what you mean.
you get what I'm saying.
Yeah, so it's, they're not, it's not like you add them up and then take the absolute value of it. The absolute value or the modulus of each of them is the same number because
Right.
they're complex conjugates. And so 0.0385 is the modulus of lambda 1, and so that's exactly the same.
Here's how I'll write.
And the modulus of lambda 3. That's what those values are.
Right.
So when you compute the modulus, as Dylan and Amelia, they can hear me.
Can you guys hear Professor Centron? Kind of. Yes. So, not very well.
Can you hear me now?
Yes. Yes, from everybody.
Okay, so I think now I'm below one of the ceiling microphones. So when you compute the modulus, that's a way to sort the eigenvalues by the value of their modulus. It's like sorting by the absolute value. So there's definitely one of them that is larger in modulus than 1, right? The first eigenvalue there.
Right.
You can see that R, you computed this with R, with the eigen command.
Right.
So R outputs this already sorted or ordered by, it seems the one that's listed first is always the one largest.
I ended up doing some variable, I think Z is equal to the eigen of that matrix. And then if you do eigen $ values, you get the eigenvalues and I'm sorry, Z $ values will give you that. But if you just do eigen, I think it also will just add.
It also works, okay.
So anyway, so I determined that this first value was the dominant eigenvalue because if you put on the numerator and then take the sum of the other eigenvalues on bottom, you see that it's greater than 1.
Yeah.
So I think that was the correct test to see which one was the dominant eigenvalue. So that means that the limiting distribution for basically for the fractional amounts of the population is going to be equal to this vector, except for you have to divide this by, I don't think I have it written down.
Okay.
You have to divide
Okay,
this
so
by
that
this
vector
number.
does it have negative values? No. And what you need to do is normalize it, right? So you need to compute the total of the entries and then divide each entry by the total so that then you create a new vector.
That's what I have here. I divided.
We cannot see. You need to move the notebook or
Oh, I'm sorry.
zoom exactly now.
So
Okay.
this is the actual eigenvector that I've played it sideways just because I feel like
Yeah, better.
makes more sense. And then I don't think I have it written, but this is what happens whenever I took the total of all these values and then divided the entire vector by that total.
So you normalize it, created another vector, and now that new vector has entries that add up to 1.
Exactly.
They add up to 1.
These
Right?
will be the if I were to consider this is like, let's just compare it to that fish population.
That's right. So group 1, group 2, and group 3, you now have the values. Now you write that in words there, group 1, group 2, and group 3, and they're each of those limiting values. Each of those is the value of that group in the limit, but is the value of the density, or what do you say, the mass fraction, or the, use the word there.
I think I said fractional population or something.
Fractional
like
something
It's
mass.
just like group 2 is going to be 21.4% of the population as you iterate it more and more over time.
Group 1, group 2, and then group 3.
Yeah, so I still have to write group 3.
You need to push that a little upward so we can see. Okay. So you have so that idea of like limiting distribution is a limit for the proportions